Good afternoon, Faisal Hussain sir, and my dear
Good
students.
afternoon.
Sir, I welcome you for the continuation of this lecture series, which is approved by AICTE under Prerana scheme. Thank you, sir.
Thank you, ma'am. So, first of all, good afternoon to all the students. I am sharing my screen now. So, this is the last lecture related to theory of machine plus vibration. And today, in previous class, we have studied about freed vibration, then the different types of energy methods, equilibrium method, then Rayleigh's method, then energy method to determine the natural frequency of the system. Then we have seen the longitudinal vibrations and torsional vibrations, transverse vibrations, how to determine their natural frequencies that we have covered. Then we have also seen what is whirling speed of shaft. Okay. And then we have covered some gate numericals. So today in the second part of vibration, we have to cover damped vibrations, then logarithmic decrement, then what is force vibration, force damped vibration, then the concept of magnification factor, vibration isolation and transmissibility. Then we will move toward the rotor system, and at last we will cover some numericals. So let us start now. Now damped vibration. Basically, what is damped vibration? As you can see, whenever any elastic body is set in a vibratory motion, slowly the vibrations die out with respect to the time, and this is because of intermolecular friction and the friction of medium in which it vibrates. So in damped vibration, there is a mass, it is a spring, mass and damper system. In free vibration, you have seen only spring and mass system. Here in this figure, you can see that there is a damper and it consists of a cylinder and a piston. Actually, it is a dashboard. There is a spring and a mass system. Now, basically, what is the purpose of damping? The basic purpose of damping is to diminish the vibrations with respect to the time. It is the basic purpose of damping. So generally external damping can be increased by using dashpot and dampers. And as I have told you, this dashpot is a piston which moves inside a cylinder. You can see this to and fro, vertical to and fro motion, and here there is some fluid which is filled in it. The best example for such type of vibration is your shock absorbers. Okay, in shock absorber, in this image you can see that the piston is continuously, due to the shocks, the piston is continuously, it is reciprocating in to and fro manner or in an up and down manner, and the fluid is playing the intermolecular friction role. So generally in shock absorbers, the movement of spring is reduced when there are sudden shocks, thus damping out the bouncing which could have occurred otherwise. So this is the basic example of shock absorbers, and it is under the damped vibration condition. Okay, now, so what is damped vibration? In damped vibration, it is a damper which has been attached to the spring mass system, and the basic purpose of dampers is to diminish the vibrations with respect to time. Now let us see this diagram and let us see how the equations are formed in damped vibration. अब यहाँ पर आप देखिए, let us see here in this diagram, a spring mass system is given with damper. This is your spring, this is your damper. So here in this direction, the spring force or restoring force will be developed upward, because the displacement is in downward direction. If displacement is downward, so velocity will be downward, then acceleration will also be downward. So accelerating force is downward, so the inertia force will act upward. So here the inertia force will be there. Okay, and similarly this is your damper. So here a damping force will also be developed, which will be in upward direction like this. Okay, so when the mass moves from its mean position, this is the mean position of the mass. Okay, when the mass moves from its mean position and it covers a distance x, at that time during a certain duration of period, then restoring force will act upward, the damping force will act upward, the inertia force will act upward, and according to the D'Alembert principle, I can sum up all the forces, inertia plus damping force plus restoring force, equal to what? Equal to 0. So this is the equation for damped vibration. Okay, where m is the mass suspended from the spring, s will be your stiffness, x is displacement. Here a damping coefficient is there. Damping coefficient means damping force per unit velocity. So this is your damping coefficient c. C is your damping coefficient and it is force per unit velocity. Similarly, omega n will be the frequency of undamped free vibrations, and x dot and x double dot will be the velocity and acceleration of the system. Now let us move further. So in the previous slide we have seen this equation, mx double dot mx double dot plus cx dot plus sx equal to what? 0. So this equation can be represented as x double dot plus c by m x dot plus s by m x equal to what? 0. I have taken m from here, from acceleration, from inertia, I have taken this m as common. So this is my equation. Okay. Now, basically, this equation x double dot plus c by m x dot plus s by m x equal to 0, this is the differential equation of second order. And if it is a differential equation of second order, then after solving this equation, we will get this relation. And this relation is x equal to a exponential raised to power alpha 1 t plus b exponential raised to power alpha 2 t. Here a and b are some constant. Okay, and alpha 1 and alpha 2 will be the roots of auxiliary equation. When you solve this equation, when you will solve this equation, differential equation of second order, you will get this equation, and from here a b are the constant and alpha 1 and alpha 2 are the roots of auxiliary equation. So this roots of auxiliary equation can be written as alpha square plus c by m alpha plus s by m equal to 0. And here the expression for auxiliary equation alpha 1 and alpha 2 is minus c upon 2m plus minus under root c by 2m the whole square minus s by m. Here I have just shown you the final equation so that we can save our time and we can complete the total damped and damped force vibration topic. Okay, so after solving this we will get this equation. Now if in this equation alpha roots of auxiliary equation alpha 1 and 2, the ratio of c by 2m the whole square and this ratio c by 2m the whole square and s by m, this ratio, its square root represents what? Represents degree of dampness. Now what is degree of dampness? Actually, degree of dampness is a damping factor or a damping ratio which is denoted by zeta. So, if I will take the square root of this factor, c by 2m the whole square, with s by m, so I will get the damping factor or zeta. So generally, this equation can be rewritten after solving. It can be rewritten as c upon 2 under root sm, where here c is your damping coefficient, c is your damping coefficient, and s or k, it is your spring stiffness. S on K is your spring stiffness, okay, and M is the mass. So this equation C by 2M the whole square by S by M can be, if we will solve it, we will get C upon 2 under root Sm, okay. Now in this equation, as I have told you, this C is your damping coefficient, and damping coefficient is defined as the ratio of force per unit velocity, and its unit will be Newton per meter per second or Newton second per meter. Also, the damping coefficient can also be written as, here you can see C is 2 zeta under root S into M, which is equal to 2 zeta m into omega n. Omega n is what? Omega n is your natural frequency of free vibrations. So I can write again this equation as 2 zeta s upon omega n. In other words, the damping factor or damping ratio zeta can be defined as the ratio of damping coefficient to the critical damping coefficient. So, if I will sum up this damped vibration, I can say that the value of damping coefficient which makes a radical zero is called as critical damping coefficient, and similarly the corresponding value of damping coefficient C is denoted by what? Cc. So in numericals also, this damping factor equation, damping coefficient equation, and the relation between damped natural frequency of damped vibration and natural frequency of free vibration with respect to damping factor is also important. So these equations are very important while solving the problems related to damped vibrations. Okay, so here what we have done, we have seen the damping factor. This damping factor has been derived from this equation, okay, and this equation, the roots of auxiliary equation is come with the help of our energy method, that is mx double dot plus cx dot plus sx equal to what? 0. Okay, now let us go to our next slide. Now as we know that we have seen this relation, x double dot plus c by mx dot plus s by mx equal to what? 0. And in this relation, what I am doing, in the previous slide, we have seen that what is C? C is what? I can write C as 2 zeta m omega n. Here I can write C equal to 2 zeta m omega n. So what I am doing? I am taking m to the denominator. So C by m will be what? C by m will be here C equal to 2 zeta m into omega n. So what will be C by m? C by m will be 2 zeta omega n. So here instead of C by m, we are substituting 2 zeta. Instead of C by m, we are substituting here 2 zeta omega n. And similarly, natural frequency is what? Natural frequency is k by m, or h by m under root, or omega n square equal to k by m, and omega n equal to under root k by m or h by m. ठीक है? So what we are doing, instead of h by m, we are substituting what? Omega n square, natural frequency. Okay. So if we will solve this equation, we will find that the roots alpha 1 and alpha 2 of, if we will solve this equation, we will find that the roots alpha 1 and alpha 2 may be real, it may be imaginary, or it may be equal. So if the roots alpha, by solving this equation, we can come into the conclusion that the exact solution of this above equation will depend upon roots alpha 1 and alpha 2. Okay. Now what will happen? If the roots are real, then the system is overdamped system. If the roots are imaginary, then the system is underdamped system. And if both the roots alpha 1 and alpha 2 are equal, then it is a critical damped system. Now if the roots condition of roots real, imaginary, equal is deciding the system, then question arises that what is critical damped system, what is overdamped system, and what is underdamped system. So in critically damped system, the system moves as quickly as possible toward equilibrium without oscillating about the equilibrium. It means that the system will come to its original position with the shortest possible time. Then what is overdamped system? In overdamped system, the system moves slowly towards the equilibrium. And what is underdamped system? In underdamped system, the system moves quickly to equilibrium but will oscillate about the equilibrium point or about the mean position. And then slowly the damping will be reduced and the system will come to the rest. Okay. So let us project some more light on this damping factor concept. So we will move to the next slide. Here see, in this video you can see there is an overdamped system here. This is your overdamped system, this is your critical damped system, and this is your underdamped system. So see, in underdamped system, slowly the system is coming to rest. In critical damped system, with the shortest possible time, the body comes to the rest. And in overdamped system, the body comes to the rest and motion is not periodic. So first of all, let us see if the damping factor is greater than 1. If damping factor is greater than 1, the system is what? Overdamped. And in overdamp, I have told you the roots will be real. Roots means what? Roots of auxiliary equation. And roots of auxiliary equations are alpha 1 and alpha 2. These are the roots of auxiliary equation. The magnitude in overdamped system, the magnitude becomes 0. So the motion is not periodic and no vibration occurs or ensues. For example, the doors. So you can see the doors of the shops. It is a overdamped system. Okay, there is no vibration. We will apply the force while opening the door, and we will enter in the shop, and then we will release the force. It will slowly, it will not vibrate, but it will slowly come to its position. So the motion is not periodic and no vibration occurs. You will never see that in the shop doors. It is when you have released the force, it is continuously vibrating. It is not like that. Okay, so it is overdamped system. Practical example. Similarly, the system cannot vibrate due to overdamping, and x means the amplitude approaches to zero with no time. Now see in this graph, you can see that when zeta is greater than 1, when zeta is greater than 1, the system is what? Overdamped. And during overdamping, you can see that the system is not oscillating, it is not vibrating, it is slowly through this curve. In this curve, you will find slowly the damping is going on, and with respect to the time, the amplitude of x is reduced. Okay. Now second is when damping factor equal to 1. Okay. अब damping factor equal to 1 है. Now here if damping factor is 1, damping ratio is 1, it means the roots are equal. Equal means alpha 1 is equal to alpha 2 of roots of auxiliary equation are equal. It means in this graph you can see that if when damping factor is 1, the displaced mass here, the displaced mass returns to its position with the shortest possible time. This is your signature during critical damping. The best example, it means that there will be no oscillations. The best example is large guns. When large guns are fired, during large guns firing, after firing, the gun recoils. Okay, and when the gun recoils, within shortest possible time, it the recoil of gun is completed. So recoil of gun, large guns firing comes under the critical damping. Okay, एकदम से झटका नहीं लगेगा आपको. Now the third category is the underdamped system. Now what is underdamped system? Your normal system. For example, let us take the example of shock absorbers. Okay, so it is an underdamped system. Here roots are imaginary. Alpha 1 and alpha 2 are imaginary, and the resultant motion is oscillatory type with decreasing amplitude. Here you can see in third category, when zeta is damping factor is less than 1, you can see that the resultant motion is slowly the displacement is reducing, and at one time it will come to the rest following SHM path. Okay, so this is the third category when damping factor is less than 1. And what happens if damping factor equal to 0? If damping factor equal to 0, it means it is a free vibration. It is not a damped vibration system. It is a free vibration system. Okay. So now let us move to the next slide. Logarithmic decrement. So basically, logarithmic decrement, for example, this is the displacement and this is my time period. Okay. So basically, in the third category, that is your underdamped system where the value of zeta is less than 1, the nature of the amplitude will be somewhat like this. Okay, so logarithmic decrement means the ratio of two successive oscillations, or I can say that It is the ratio of two successive oscillation on one side of a mean position. For example, if this amplitude is xn, on the same side of it, if it is x1 n, then the ratio will be constant. So the ratio of two successive oscillations is constant in an underdamped system, and logarithmic decrement can be defined as the natural logarithm of this ratio. Which ratio? Ratio of two successive amplitude. If I will take the ratio of these two successive amplitude with respect to its natural logarithm value, then I will get the logarithmic decrement. Here I will get the logarithmic decrement. Okay, so logarithmic decrement can be written as natural logarithm exponential raised to power zeta omega and td, where td is what? Time period, time taken to complete one cycle. And again it can be represented as zeta omega n into td, as td is what? Td is time period, time taken to complete one cycle, and td means your time taken during damped vibration. So here it will be omega d. Okay, so instead of td, if I will substitute 2 pi by omega d, okay, so this will be the relation zeta equal to logarithmic decrement equal to zeta omega n, and instead of td I have substituted 2 pi upon omega d, which can further be substituted as zeta omega n upon 2 pi under root 1 minus zeta square into omega, and finally it can become 2 pi zeta under root 1 minus zeta square. So this is the expression. These are all the expressions of logarithmic decrement. Okay, now let us move to our next slide, that is the forced vibration. This is the after damped vibration, it is forced vibration. So for in forced vibration, the forcing is incorporated in three parameters. Okay, the first parameter, 1 minute. Okay, the first parameter is your step input forcing. Now in step input forcing, application of constant force to the mass of a vibrating system is involved. It means that if a constant force is applied on the vibrating system, it comes under the category of step input forcing, and the equation will be inertia force mx double dot, plus your restoring force equal to the constant force F. Second is your harmonic forcing. In harmonic forcing, what happens? A oscillating force. In this diagram, in this figure, you can see that this is the oscillating force. Fo sine omega t is applied on the system. So this figure, in this figure, there is a spring mass system. The mean position is BB or BB dash, and when before the mass is set in motion, BB dash is the static equilibrium condition. Okay, under the weight of the mass, and when an oscillating force Fo sine omega t is applied, the equilibrium condition is disturbed, and now the body is displaced, and the axis is C dash. Now the mass is on the axis C dash. The position is displaced of the mass. So here, as displacement is downward, restoring force Kx or Sx will be upward. Inertia force will be opposed to the oscillating force, and it will be upward, and downward will be your oscillating force. So what will be the equation? Equation will be inertia force plus spring or restoring force equal to upward force equal to downward force equal to your impressed oscillating force. Okay. I can also write this equation as Fo sin omega t minus mx double dot minus sx equal to 0. Now, the equation mx double dot plus sx equal to Fo sin omega t, the solution for this equation will consist of two parameters that you have studied in your mathematics, that is your complementary function and the particular integral. Okay, so the complete solution will be CF plus PI, and then we can find the equations for the above term, also for the above parameters, that is your spring, that is damage spring and the oscillating force. Now the third one is your periodic forcing. So generally periodic forcing is what? In periodic forcing, the motion will repeat itself in all details, and after a certain interval of time, again it will be repeated. So there will be repetition of motion after certain interval of time. So it is known as a periodic forcing. So these are the three types of forcings incorporated in forced vibration. Step input forcing, where constant force is acted. Harmonic forcing, where a simple harmonic nature force, oscillating force is applied. And third is your periodic forcing, which is applied continuously through a certain duration of time. Okay. Now let us move to a forced damped vibration part. Now see students, here in this figure you can see a spring mass system and a damper, and this is the free body diagram. Now as we are discussing with the free body diagram, this is your oscillating force Fo. So it is under simple harmonic condition. Okay. Then this is your damper. So the damping force will be Cx double dot, and this is your stiffness. So spring force or stiffness force Kx or Sx will be this. So through free body diagram, direction upward, inertia force direction upward, and this is your downward direction. So here through the equilibrium method, I can say mx double dot plus cx dot plus sx equal to Fo sin omega t. And in the previous slide we have discussed that it is a simple harmonic forcing concept. So the solution for this equation will be in two parts, that is CS complete solution will be CF complementary function plus particular integral. So when we will solve the above equation, that is your mx double dot plus cx dot plus sx equal to Fo sin omega t, when we will solve the equation, the complementary function will be Cf equal to amplitude x e exponential raised to power zeta omega n t. This is omega n, this is minus zeta omega nt sin omega dt plus phi 1. This is your lag period, and the particular integral will be pi will be Fo by m under root s by m minus omega square the whole square plus c by m omega the whole square. After solving it, we will get this equation, and when I will again solve it, I will find Fo will be under root s minus m omega square the whole square plus cw omega square sin omega t minus phi. So the complete solution after finding complementary function and particular function the complete solution X will be CF plus PY. This is your CF and this is your PI. Okay. Generally what happens in damped free vibrations represented by the first part, that is your complementary function, and it becomes negligible with respect to time. So generally this CF is negligible with respect to time, so it will be 0. So this term will be 0. So the complete solution will be equal to particular integral, and it will be just FO upon S minus M omega square the whole square plus C omega the whole square under root into sine omega t. So finally I can conclude in this slide that the steady state response in terms of the amplitude for the system, steady state response of system is only represented by the second part, that is your particular integral. Okay, this complementary function with respect to the time, it is negligible with, okay, and it will be 0. So this is the equation for steady state response of a system. Now what is amplitude of steady state response? Here, as we have seen that FO upon, this is your particular integral, this is the steady state response equation. वही इक्वेशन मैंने यहाँ पर लिखा हूं, and if I will expand this equation, I will get that amplitude of steady state response is FO by S upon under root 1 minus omega by omega n the whole square plus 2 zeta omega by omega n under root. So this is the amplitude of steady state response. Here you can see that this amplitude A of steady state response depends upon two parameters. One is your omega by omega n frequency ratio, and another one is your damping factor zeta. Okay, it means that if the damping factor and the frequency ratio factor, okay, if they are increased, amplitude will reduce, and if these two factors are reduced, then amplitude will be increased, vice versa. And this amplitude of steady state response is in this equation is in dimensionless form. And if it is in dimensionless form, it is more convenient for analysis. Here you should keep one thing in mind, that this FO by Fs, this relation, this FO by Ss is what is your static deflection of the spring stiffness under oscillating force FO. Also, with addition to the amplitude of steady state response, there is a phase angle also, and this phase angle or this phase lag depends related to the displacement, which is directly related to the velocity vector. And the equation for phase lag is tan psi equal to 2 zeta frequency ratio upon 1 minus frequency ratio square. Okay, now the phase angle is denoted by phi. It is generally a phase lag. Now see, in this slide what we will do, we will see that how the vector diagram and phase diagram is completed. As in the previous slide, I have discussed about the phase lag. Phi. Phi is what? Phase lag for the displacement relative to the velocity vector. So now, as we know that mx dot plus cx dot plus sx equal to FO sine omega t. Okay, here if we will find the displacement with respect to simple harmonic motion, we know that amplitude x equal to a sine omega t minus phi, because minus phi because of phase lag. If there is no phase lag, it is a sine omega t. Okay, so as there will be a phase lag, so displacement will be A sine omega t minus phi. If this displacement is differentiated with respect to time, we will get the velocity x double dot, and it will be omega a sine pi by 2 plus omega t minus phi. And again, if it is differentiated with respect to time, we will get the acceleration minus omega square a sine omega t minus phi. Now here, if we will substitute the value of x double dash, x dash, x dash in this equation, and if we will rearrange the terms, my first term is fo sine omega t, my second term is mx double dot, and if I so this mx double dot, so what is acceleration minus omega square a sine omega t minus phi. If it is transferred here, for example, fo sine omega t minus mx double dot minus cx dot minus sx will be equal to 0. Okay, so minus minus will become plus, and this equation will be m omega square a sine omega t minus phi. Similarly, the damping force Cx dot will be minus C, and instead of x we have substituted omega a sine pi by 2 plus omega t minus phi. Okay, so we have substituted this minus, and x double dot value becomes plus. And then the last one is your restoring force S into x. So instead of x I have written a sine omega t minus phi. So this is my equation. Now let us draw the phase diagram. Here in this phase diagram, we will, for example, this is your x axis, and this is your y axis. These are two axes, x and y. Now first of all, the first force is your oscillating force Fo. So here Fo, oscillating force with respect to the angle omega t. So I can draw this force, it is at certain angle. This is my oscillating force, maximum oscillating force Fo. Okay, so this direction is of Fo, oscillating force. Now second is your m omega square a, and this Fo is at an angle of omega t. This Fo is at an angle of omega t. Now the second is m omega square is sine omega t minus phi. So the phase lag is phi. So this is your phase lag phi. This angle is your phi. I will try to draw with another color. Okay. This phase angle is phase lag is phi. So if this is omega t, this is phi, so this will be omega, this angle will be omega t minus phi. This is your omega t minus phi, and here this will be your m omega square into a. This is your maximum accelerating force, maximum inertia force, sorry. Now after that, minus c omega a, this is your damping force, and it is at an angle of pi by 2. Pi by 2 means what? 90 degree plus omega t minus phi. So this is omega t minus phi. This line is at omega t minus phi. So omega t minus phi plus 90 degree. So this will be the 90 degree. So from here, this angle is 90 degree. Okay. Now why we have not drawn the inner direction of inertia force upward? Because here you can see that it is minus CW. It means it will act in opposite direction. So the direction will be downward. Its direction is downward. That's why it is acting in opposite direction. And the last one is your the restoring force omega t minus phi. So if this is omega t minus phi, if this angle is omega t minus phi, okay, so restoring force will also be in this direction, but it is also minus. It is also minus, so opposite to it. opposite to it, equal and opposite to the inertia force. This will be the direction of, okay, omega t minus phi. So this is your restoring force. So from this figure you can see that inertia force, damping force and your restoring force, all the three forces are mutually perpendicular. And if I will I will assume the omega in anti-clockwise direction, okay, my first force is, tell me, the first force is FO. Now see the vector diagram, this is FO, this direction is FO, parallel to this. After FO, I am referring in anti-clockwise direction. Next is your SA. So parallel to SA, this is the vector diagram of SA. Similarly, third one, after this, we are seeing in anti-clockwise direction, this is C omega A. So this is your C omega A. And after C omega A, that is your damping force. The last is your inertia force. So this is your inertia force. So this completes the vector diagram. If this distance is m omega square A and this distance is SA, and if I will drop a perpendicular here, so this distance will be what? This distance will be SA minus m omega square A. So this completes your vector diagram and this is your phase diagram. So through this equation, we can draw the vectors as shown in the diagram, which are fixed relative to one another and rotate with angular velocity omega. And here what we have assumed, that the displacement, see, we have assumed that the displacement of the vibrating mass under the action of the applied simple harmonic forcing is also simple harmonic and lags by an amount phi. That is your phase lag. Okay. Now, magnification factor. So what is magnification factor? Magnification factor is defined as the ratio of amplitude of steady state response to the static deflection. Ratio of amplitude of steady state response to the static deflection under the action of force FO is known as the magnification factor. Clearly you can see that the magnification factor depends on frequency ratio and zeta, like the amplitude of steady state response. So magnification factor depends on frequency ratio and your damping factor. Now let us move to the next slide. Here there are two graphs. One is the graph between figure A. This is the graph. This is the graph between magnification factor and frequency ratio, and figure B is the graph between phase angle and frequency ratio. So in this graph, directly you can see that here in figure number A, you can see that the curve shows the damping. Means that here, if damping factor increases, magnification factor is reducing, and if magnification factor and if damping factor is increasing, magnification factor reduces, damping factor reduces, magnification factor increases. Here on y-axis, this is your magnification factor. This is your magnification factor, and x-axis it is your frequency ratio. Also, in this graph we can see that when there is no damping, it means that zeta equal to what? 0. Okay, if zeta is 0, the magnification factor reaches to what? Infinity. And if it reaches to infinity, it means that the frequency of force vibration will be equal to the frequency of free vibration. Resonance will be occur. Okay. Also, रेजोनेंस तो आ रही है उसमें, साथ ही साथ में In figure number B, we can also see that in figure number B, this is your phase angle and this is your frequency ratio. Here see, the phase angle varies from 0. The phase angle varies from 0 at low frequency to 180 degree at very high frequency. So it is changing very from 0 to 180 degree. The phase is changing very rapidly. And at the resonance point, this is the point where resonance takes place. It is at 90 degree. At 90 degree, irrespective of damping, there will be a resonance. Okay. Also, we can see that the damping ratio, irrespective of the amount of damping, maximum amplitude of vibration occurs when it is occurring when the frequency ratio reaches to unity. See, this is unity. This is unity. Omega by omega n equal to unity. So when omega by omega n frequency ratio reaches to unity, then frequency of force vibration will be less than that of the undamped vibration. So through this graph A and graph B, we can see that how the resonance is occurring, and similarly we can also see that how rapidly the frequency ratio changes with respect to the phase angle from 0 to 180 degree. Now let us move to the next part, vibration isolation. In simple terms, I can say that it is a technique which is used to diminish the transmitted forces. Now, in every structure, there is a foundation, and when it may be a structure or a equipment, okay, when the equipment is in working condition, forces will be transmitted, and those forces will be transmitted to the ground. So, there is a foundation, and in between foundation and the structure, there is a isolated device or isolating object, and it is in between the structure and foundation, and this isolating device is used to reduce the transmitted forces which can be transmitted from the structure to the foundation. So the isolation in this diagram also, here you can see that there is a structure and here there is a foundation, and between them is an isolation device. This isolation device, the main purpose is to diminish the transmitted forces which are coming from the structure to the ground. Okay, and if we will zoom this isolation device, it is like this. There are number of rubber layers, and between them there is a steel plates which are used to absorb the transmitted forces. Okay, so over briefly, I can sum up the vibration isolation by saying that vibration isolation is a process of isolating an object, and it is a technique which is used to diminish or reduce the transmitted forces coming from structure to the foundation. This isolation device is attached between the upper structure and the foundation, and it will reduce the transmission of vibration energy. And there are different types of vibration isolation available in the market. Rubber isolations are there, sliding isolations are there, hybrid isolations are there, depending upon their use. Now, vibration transmissibility. So, as we have seen in the vibration isolation, when the structure or equipment will be in operating condition, forces will be transmitted. So, the ratio of force transmitted to the foundation with respect to the force applied is known as the vibration transmissibility. It is the ratio of Ft by F0. Here you can see the expression. Ft is the force transmitted, okay, to the foundation, and F0 is what? F0 is the force applied. So the ratio of these two parameter is known as transmissibility, and its equation is under root 1 plus 2 zeta omega n by omega n the whole square divided by under root 1 minus omega by omega n the whole square plus 2 zeta omega n upon omega n the whole square. This is the equation, very important equation related to gate numericals. And please keep two things in mind, that when at resonance the frequency ratio will be n, and if the frequency ratio at resonance is 1, the transmissibility relation is this one. epsilon equal to under root 1 plus 2 zeta the whole square upon 2 zeta. And if there is no damper, it means the damping factor is 0. If the damping factor is 0, zeta will be 0. Okay. And if zeta will be 0, on the numerator there will be only 1, and on the denominator there will be 1 minus omega n upon the whole square plus minus. So these are the equations for transmissibility, the basic equation at resonance condition and when zeta equal to 0. Now let us see this graph. It is the graph between transmissibility ratio and the frequency ratio. Here we can see that if the frequency ratio is less than root 2, this is my point root 2. Okay, this is point root 2. If the frequency ratio is less than root 2, it means that the transmissibility ratio will be more than 1. Here the transmissibility ratio will be more than 1. Okay, and if it is more than 1, transmitted force is always more than the excited force, means Ft will be more than Fo. If the frequency ratio is greater than root 2, then the transmissibility value will be less than 1. Here the value will be less than 1. It is below this line. And if it is so, then transmitted force is always less than the exciting force. And if the frequency ratio is root 2, it means that the transmissibility is 1. And if transmissibility is 1, Ft will be equal to what? Fo. And if the frequency ratio is 1, then at that position, the transmitted force will be infinite. So the overall conclusion from this graph is that in a system, the frequency ratio can vary from 0 to higher values. Dampers should not be used. Instead, stops or stoppers may be provided to limit the resonance amplitude, because at resonance the amplification factor is infinitely. Okay. Now rotor system. So in a previous lecture of vibration 1, we have seen the torsional vibration. So this is the part of torsional vibration. Here it is a free torsional vibration of a single rotor system. This is your shaft at one end. This is your rotor, and other end is fixed. When the rotor, when the rotor is applied a torque, or if the rotor is rotating, or if there is a torsional twisting moment of the rotor and torsional untwisting moment of the rotor, this will be the noding diagram. Okay, this is the rotor is twisting and untwisting like this. So what will be the frequency? Frequency we have seen Fn is what? 1 upon, actually it is 1 upon 2 pi. 1 upon 2 pi under root Q by I. And instead of Q, I can write Cj upon L. This is your L and this is your I. So this is the equation. Here you can see when the point where shaft is fixed, here there will be no frequency. And if there is no frequency, the point is known as node. Here there will be no frequency, no displacement. And at the free end, there will be the maximum amplitude of frequency. Then the rotor system, free torsional vibration of a two rotor system. Here see there are two rotors which are mounted on the same shaft. Okay, this is shaft number, this is your rotor A, rotor B. Now let us assume that rotor is rotated in clockwise direction and rotor B is rotating anti-clockwise. It means both the rotors are rotating in opposite direction. So here it will behave like a cantilever position. One minute, like this. Here, if both the rotors are rotating opposite direction, at the center there will be no deflection. And if at the center there will be no deflection, this is your noding diagram. So at this point there will be node and here frequency will be 0. So what we are doing, the natural frequency equation is what? Fn equal to 1 upon 2 pi G into J divided by I into L. This is the frequency equation. So frequency at rotor A is this, frequency of rotor B will be this. Okay, from node let this distance be LA, and from node let this distance from rotor B. For example, this is A and this is B. So let LB be the distance of node from rotor B and LA be the distance of node from rotor A. As both the rotors are mounted on the same shaft, therefore Fn frequency of A will be equal to frequency of B. If you will substitute, 1 by 2 will be get cancel, root cancel. Okay, modulus, shear modulus, that is your C. It will get cancelled because only one shaft, one material. Shaft has a uniform diameter. So here it will be IALA equal to IBLB. So I can write LA equal to IBLB upon IA. And also here this is the total length. So what will be the total length? Total length will be LA plus LB. So by solving equation 1 and 2, we can find the frequency. We can find the frequency of the rotor, of a two rotor system. Now, three rotor system. Here there are three rotor system. Let us consider a shaft of uniform diameter D. This is the shaft having uniform diameter. Rotor A and B are rotating in opposite direction. B and C are rotating in opposite direction. So between rotor A and B there will be one node, and between rotor B and C there will be other node. At the center it will behave as a cantilever. Okay. So now this is your point B, this is your point A, and this is your point C. As all the three rotors are mounted on the same shaft, it means frequency of A will be equal to frequency of B will be equal to frequency of C. And by solving these three equations of frequency, we can determine the positions of node. We can determine LA and LC, and also we can determine the frequencies of the system. Now see, Fn, the basic equation is 1 upon 2 pi Gj by I into L. Okay. So G is your C, this is your C and G are shear modulus. Okay. If I am considering rotor A, this is my equation. If I am considering rotor C, this is my equation. But at point B, at rotor B, there are two nodes on either side. So its equation will be Fnb equal to 1 by 2 pi under root Cj upon Ib 1 upon LA minus LA. This is the distance L1 minus LA, and this is the distance L2 minus LC. This is your another distance. Okay. So after equating these two frequencies, we can find the answer. Now there is a equivalent shaft. What is equivalent shaft? Actually, it is a generally what happens in actual practice, there may be shaft having variable diameters for different length. Okay. But if we are finding the frequency, it is not possible to consider all the sizes of the shaft. So what we do, we generally reproduce the shaft of varying diameters into a torsionally equivalent shaft in such a way that the twist will remain same as that of the actual shaft with actual length. Okay. And when equal and opposite torques of given amount are applied, all the parameters regarding the twisting will be same. So this is the diagram here. There are different cross sections of various sizes, and there are two rotors and a twisting torque is applied on it. So we have converted this shaft of varying diameter into a equivalent shaft diameter. Here we can assume the equivalent shaft diameter equal to size of any of this shaft. You can assume D equal to D1 or equivalent diameter equal to D2 or equivalent diameter equal to D3. You can assume any of it. Okay. And then we can find the frequency of the system by using this equivalent length equation. L equivalent equal to L1 plus L2 D1 by D2 raised to power 4 plus L3 D1 by D3 raised to power 4. Okay. So this is the briefing of equivalent shaft. And the last is your free torsional vibration of a gear system. Here a gear system between two rotors. Okay. There is varying shafts attached, and similarly in between there is a gearing system. This is your pinion and this is your gear. A gear attachment is given, non-intersecting condition. Okay. Here three parameters or three assumptions have to be known. First is that inertia of gears and shaft is negligible. Load is within elastic limit of gear teeth, and there will be no backlash or slip occurs in the gear drive. Generally, problem related applications related to centrifugal pumps, such type of conditions arrive in gear system, torsional vibration of gear system. Best application is centrifugal pumps. So here also, if you want to determine the frequency of the system at rotor A and rotor B, two things we have to sum up. One is the kinetic energy of equivalent system should be equal to the kinetic energy of the original system. And second, strain energy of the equivalent system will be equal to the strain energy of the original system. These two conditions we have to sum up, and after solving these two conditions, we can determine the frequency of the system. So this is the concept of geared system related to torsional vibration. Okay. Now let us solve some numericals related to the damped vibration. The first numerical is that the damping ratio for a viscously damped spring mass system is governed by the relation m at d2x plus c dx plus ks. Actually, it is d2x means x double dot. This is your c x dot, and this is your kx, which is equal to f of t force vibration. Okay. And what we have to determine? We have to determine the damping ratio. See, I have given you the hint, and damping coefficient is what? C equal to 2 zeta under root s by m equal to 2 zeta m omega n. So as C equal to 2 zeta, as C equal to 2 zeta m omega n. Okay, I can write zeta as C by 2 m into omega n. So here I can write 2m, and omega n is what? Omega n is frequency. We have derived k by m, so it is k by m. Okay, so from here zeta will be, if I will rearrange this term, I will get the answer C equal to 2 root km. So this is the answer. So C by 2 root km. So option B is your correct option. Now let us move to the second problem. Here, a single degree of freedom spring mass system with viscous damping has a spring constant of 110 Newton per meter. Spring constant means your stiffness. So stiffness can also be written as S or K, and it is 110 kilonewton, that is your 10,000 Newton per meter. Then the external force FO is 100 Newton. System is excited by a sinusoidal or a oscillating force of 100 Newton, and damping factor is zeta. So zeta is 0.5 and FO is 100. Okay. And at resonance condition, at resonance, you know that omega by omega n equal to unity. It means omega will be equal to omega n. See, this is the uh, amplitude equation for a steady state oscillation that we have seen. Here FO by Fs is a static deflection. Okay. So each and every is given to you. At resonance, omega by omega n will be 1. So this will be 1. So this get cancelled. So A will be what? A will be FO by S. This square with root, it will get cancelled. Here it will be 2 zeta omega by omega n. So FO is 100. S is 10,000. 2 into zeta is 0.25, and at resonance F by Fn will be 1. So from here we will get the amplitude 20 mm. So this is the answer. So like this, the third problem here. In this problem, a single degree of freedom of mass spring viscous damper system with mass m, spring constant k, and viscous damping coefficient q is critically damped. Critically damped mean what? Solution, first of all, mass is m is your mass, spring constant is your k, and viscous damping coefficient. Okay, this is your spring constant, and viscous damping coefficient C, it is your Q. Okay, this is your damping coefficient. So C is replaced by Q. And we have to determine what? We have to determine out of 4 options, either the damping coefficient is root 2 km or 2 root km or root 2k by m or q equal to root k by m. So this we have to determine. So how we will determine? Now, as we have discussed earlier, what is zeta? Zeta is c upon 2 under root km. So instead of c, I will write q upon 2 under root km. So this implies what will be q? Q will be 2 zeta under root km. It is a critically damped system. Critically damped. If critically damped, what will be damping factor 1? So what will be my answer? F equal to 2 under root km. So F equal to 2 under root km. This is your correct answer for problem number 3. Okay. Now let us see this problem. A single degree of freedom spring mass system is subjected to a harmonic force of constant amplitude. So see here, constant amplitude is given. Okay. Now for an excitation frequency of 3k by m, okay, this is the excitation frequency 3k by n omega. The ratio of amplitude of steady state response to the static deflection. See, A is your amplitude and FO by S is your static deflection. Okay. So the question says that we have to determine the ratio of amplitude of steady state response to the FO by S. ये हमको निकालना है. And for that purpose, omega is given 3k by m. Okay. Similarly, it is static deflection and also constant amplitude. If constant amplitude is there, zeta will be 0. And if zeta will be 0, okay, this whole term will be 0. And this whole term is 0, then I can write this. I will show in the next slide. First, see what we can do. Omega n is what? Natural frequency is k by m, and omega is given. This is omega under root 3k by m, and omega n is under root k by m. Here we have to find frequency ratio omega upon omega n. So omega upon omega n, अगर अब मैं value put करता हूं तो it is root 3. In the next slide, see. Okay. Here, let us solve here. So here we have to determine A upon FO by S. So A upon FO by S will be equal to what? It will be equal to, if this is 0, FO by S को आपने शिफ्ट कर दिया ऊपर, न्यूमरेटर में 1 हो गया, 1 minus omega by omega n the whole square, like this. And here if this is condition, then we have to use plus minus, square get cancelled. So from here we will get A upon FO by S equal to, we will consider negative sign, 1 upon 1 minus and omega by omega n the whole square. So root 3 square cancel. So it will be minus 1 upon minus 2, minus sign cancel. So answer will be 0.5. So like this, we can, by using the assumptions and by using the basic concept of vibration, we can solve the problems. Okay. So in today's class, let us sum up this, that we have completed the force vibration concept. Then we have seen what is the magnification factor, what is the amplitude of vibrations, damped vibration, force vibration, and then we have covered some gate numericals. So like in 2 class of vibration, part 1 and part 2, we have completed the vibration topic also. So thanks for listening me. Thanks.
So, on behalf of the Department of Mechanical Engineering, Anjuman College of Engineering and Technology, Nagpur, I, Dr. Tanuja Vaidya, extend my vote of thanks for giving us your time, a very detailed knowledge of subject required to face the exam for the student. It was your enthusiasm. Student got stuck up to their screen. Thank you very much, sir.